It's time to start thinking long term. The next set of vector functions model real-life motion. Okay, so here's the rub. I've got one working formula at the HAB. That's problem A. Problem B is I've got a rover that has a range of 35 miles. So I've got to learn some way to determine velocity and acceleration of a vector function while inside a rover with marginal life support the size of a small van. So in the face of overwhelming odds, I'm left with only one option. I'm going to have to calculus the crap out of this. Well, velocity and acceleration are ways of looking at vector functions uh, as if they are, or actually in a way that they're modeling motion, the motion that sends rocket ships out to the stars. And so what we're going to do is we're going to try to understand that relationship between the vector functions and velocity and acceleration. So starting off, we're going to use, think of the vector function as being a position. And the r of t is just the position in 3D, in 3 space, where t is time. Anyway, velocity, this should come as no surprise to you. Velocity is just the derivative of position. And notice that velocity is a vector. So it not only has direct length, it also has direction. And the magnitude of that velocity vector is the speed of the object. So when you think of speed, that's how fast you're going. So if you're driving your car, how fast you're going is your speed. Your velocity is the direction and the speed together. So you could be going 35 miles an hour north or 35 miles an hour south, and it's the same thing in terms of the speed, but velocity, it's very different. Your direction is important. So the direction of your velocity is the unit tangent vector. The unit tangent vector is you just take the derivative, well, the velocity and divide it by its magnitude, turn it into a unit vector. We'll do this in some of the examples. Acceleration, once again, no surprise here. It's the second derivative of the position and the derivative of the velocity, of course. It's a vector as well. The direction is the direction in which the velocity is changing. So this is kind of interesting. You could be moving forward, but have an acceleration that's behind you. That's when you're slowing down. Also, your acceleration could be, as you're moving forward, could be to your side as you're going around a turn. So acceleration is how your velocity is changing, and that could be turning, slowing down, speeding up, or doing all at the same time. Well, I guess you can't slow down and speed up at the same time. So it has different components. This is just an overview. We're going to compute all of these things, don't worry. What we call the parallel component of acceleration is the amount of acceleration that's pushing you forward or slowing you down, so forward and back. The normal component of acceleration is the amount of the acceleration which is turning you left, right, up, down, however it is that you're turning. Anyway, here's the, I guess, notation, but let's get to a problem so that we can see how this all works together. And I bet you can guess where I took this one from. You can see it looks really familiar, doesn't it? Anyway, suppose I have a particle moving using this position function. I'm going to know the velocity, acceleration, and speed of that particle. So the velocity is easy enough. That's just the derivative. And if we were together in class, I would make you do this because this one's exceedingly simple. It's just going to be e to the t times I plus 2e to the 2t times j. The acceleration is pretty easy as well. Whoops. Sorry. Okay. So acceleration is the derivative of velocity. So just do the derivative of that thing up there. You get e to the ti plus 4e to the 2t times j. Not a really exciting function, to be honest. Finally, speed. So speed is just the magnitude of the velocity. So you can do this, take this and do the magnitude, which means you're going to do e to the t squared plus 2e to the 2t squared. This can be simplified some, but not much. So we're kind of stuck with e to the 2t plus 4e to the 4t is what you end up with. Like I said, you could factor out some stuff, but not much. So we're kind of stuck with that. So anyway, there's velocity, acceleration, and speed. Let's do one more example, and then we'll take a little break and for the next video. So here's another example where we're looking for velocity, acceleration, and speed. So you should be good at this now. And I've got this written as a vector function in component notation, which is totally fine. So v of t is r prime of t, and we can do this right inside the angle brackets. That's totally fine. So I have 2t plus 1, 2t minus 1, and 3t squared. Next, we'll do the acceleration. The acceleration is the derivative of velocity, and that's just 2, 2, and 6t. Finally, the speed. That's going to be the magnitude of the velocity. So I'm taking this thing right here, and I'm going to do its magnitude. So that goes down here. So getting back to the actual problem, we have 2t plus 1 quantity squared plus 2t minus 1 quantity squared plus 3t squared quantity squared. Now this one I am going to simplify because I used this same vector function for another example later on, actually in the next video. So it's going to be helpful if I actually simplify this. So let's go through the motions here. It won't take too long. Do some algebra. So we have 4t squared plus 4t plus 1. That's this thing squared. Then 4t squared minus 4t plus 1. That's that one squared. And then this is just going to be 9t to the 4th. So all of this together is going to be, let's see, 9t to the 4th plus, is that only 8? Yeah, unfortunately it's just 8. 8t squared, and then it looks like 2. So there it is. So like I said, it'll help me later on to have it. So there it is. Okay, so in the next video, we'll continue with some examples and actually get to some of the more complicated aspects of motion in 3D.